Okay, so we'll get started. So like I said, it's going to be mostly review of high school stuff at this point. Um, so I'm actually kind of humming and hawing long term about whether or not I even want to talk about this topic anymore. Like I did the graph theory thing, and people seem to like it, so I'm not like, hey, wait a minute, maybe I should examine other topics too. So this is one where I'm like, I don't know. So we're still going to go through it. Announcements, and this is more for the video because pretty sparse group today. I haven't posted it yet. I will try to tonight, which is Code Travis for tomorrow. But I do have the third project, the final project done, which is all programming. I don't want to say there's no math in it because it is connected to the math topics we've done, and you have to understand the math topics to implement the algorithm in the programming language. But it is programming. And right now, I think I have 4 questions on it. One of them is like implement a base converter. So, I type in base 12 and then base 6 and then a number, you convert from base 12 to base 6, right? And then print it out. So that's one of them. Another one is do some matrix operations like matrix multiplication, addition, that sort of thing, and with some error checking to make sure the sizes make sense, that sort of thing. The final one, though, is the one where I'm like, okay, I need to talk about this. So I'm having you implement a binary search tree structure using object-oriented programming principles and recursion. But that means you're doing all of it. So I've given you sort of the base class and all of the functions I want you to implement. And right now it would just say like, def lookup, and then right below it is pass. It does nothing. You have to implement it. But I have comments explaining like what I want you to do in them. And some of them are probably not going to take too much effort. Like building lookup is relatively straightforward. It's just a recursive traversal through a tree. Stuff like that. Once you start playing around with it, you'll really understand it. But things like deletion from a binary search tree are non-trivial. You have to worry about whether or not I'm deleting the root, whether or not I'm deleting a node with children, that sort of stuff. You have to pay attention to that. But the way I have it set up is that I have a test file. So you don't talk about unit testing until later on, like next term, I think. So I'm not asking you to write tests or even really understand what they do. All you would have to do is go to your console and you'll type in pip install PyTest, or you can use VS Code or PyCharm to install it however you want. I can show people how to do it. I will help you with it. But all the grading is done for that third question or fourth question, whichever one it is, done that way. So you'll have a test file, and all you have to do once you have that installed is you click run. And a bunch of tests will happen. It'll tell you what you failed and why. And if you pass the test, in the comments right above it, it says this is worth 2 marks. So if you pass that test, hey, there you go, 2 marks. Right. So I've set it up so that like the harder stuff to implement, one of them is like a bonus mark. One of the test cases. So if you can't do it, oh well, it's bonus mark anyway. So this is like an experiment for how I would assign a programming question like that. But the reason why I'm mentioning it is it's non-trivial. This is something that like at a beginner, like I've only done like 1 term of 1 programming class is pretty challenging. Not insurmountable. I'm not sending you something that, well, I don't know yet. Maybe I am. Maybe this is something that everyone's like, Travis, this is freaking impossible. We can't do this. In which case, fair enough. I'll adjust. Right? That's a me problem at that point. But I've asked other cohorts, like previous people who've taken this program and now they're in the 2nd, 3rd, or 4th term. I was like, hey, here's a question on a project. Do you think you could have done it? And most of them are like, well, it seems pretty challenging, but interesting. So yeah, I think I could have done it. It would have taken some work, but it looks fun. And some of them are even working on it right now because they're like, hey, it sounded fun. I want to do it. So this is more just me saying, hey, yeah, don't leave it to the last minute. And if you do, well, you made your bed. Sleep in it. Because I just said this is probably a non-trivial question and you probably want to work on it in advance a little bit. Again, just wrapping your head around some of the recursive techniques is maybe a bit more involved. Like you did do it, some of it on one of the assignments, right? You did in order traversal of a binary tree, right? So I have you do that. And then I have you do pre-order and post-order and stuff like that. And those traversals depend on your tree actually working. So that's also a difficulty of testing. I don't know. I thought it was an interesting and fun sounding assignment. So I guess we'll see. So I'm just encouraging you to look at it in advance is all. So with that said, I don't think I have anything else to talk about other than that, I guess, kind of ominous warning. That was that an ominous warning or a threat? Yeah, I don't know either. So just, I guess, a heads up of that. So anyway, we're going to talk about some probability stuff. And a lot of it is sort of just equipping you with terminology. There's a lot of terminology in probability and statistics, honestly, like so much. And we can only talk about so much. But one of the reasons why I want to talk about probability and why I'm thinking, hey, maybe I should change this around to not be probability so much as it is statistics, is because as we march towards the future, artificial intelligence is becoming a lot more important. And even just as a general programmer, you're probably going to start to need to know it. And by artificial intelligence, I don't mean ChatGPT. That's not artificial intelligence. That's autocorrect on your phone. It's really stupid and bad. But the underlying technology, language learning models, machine learning, that sort of stuff, is going to become important. And knowing probability and statistics is kind of fundamental to understanding how those work. So this is more meant to get you prepared for that eventuality. Like it's stuff you'll have seen in passing. You'll be like, oh, okay, I remember Travis talking about that. So now it's not so daunting when we talk about gradient descent, which is a multivariable calculus topic. Anyway, so let's just start with some definitions here. So another thing I'm going to end on something fun for this topic. We're going to talk about just a simulation I have made up. But this is very, for this lecture, it's very definitions heavy and dry. Next lecture is not so much, but this one is like that. And I apologize. So a random phenomenon So that is a situation where we know the possible outcomes, but don't know which one will happen. Is a situation where we know the outcomes, but not which will happen. So ultimately, that means we're not interested in the unknowable situations, right? We're talking about, hey, rolling a die, right? I roll a die, it's going to land on one of those 6 faces if it's a 6-sided die, right? And you might say, aha, Travis, well, what if it lands on its corner? Well, I would call that a failed trial, and you would do it again, right? That's not a valid outcome, right? It doesn't mean anything. Sort of like if you flip a coin and it lands on its side, the answer is not, aha, well, I won either way. It's like, no, flip the coin again, right? So we're just saying, hey, we're only going to know, we're going to care about situations where we know the possible outcomes that could happen, but just not which one will happen, right? Could be any of them. So observations of these are called trials. And if we record it, we call that its outcome. So we're not actually interested specifically in trials necessarily. We're interested in collections of them, right? You do, a trial would be I rolled a die, it came up 5. So writing that down, well, that's trial. I did a trial and the outcome was 5, right? But we're interested in, broader scope things, right? Okay, I could roll a 5, but I could also roll a bunch of other things. So what if I wanted to roll an even number, right? What's the chance of that happening? What's the chance of me rolling less than 5? That sort of stuff, right? So an event is what we're really interested in, is a collection of these outcomes. And generally speaking, we represent events with capital letters, which there are several other things that we represent with capital letters so far in this course. And we're saying a collection of these outcomes, which should tell you what we're talking about. We're talking about sets. These events are just sets. So suppose we do such a trial. So there are n possible outcomes. Right? And we also assume that they're all equally likely. That's not necessarily required, but for our purposes, it's going to make it easier, right? If they're not equally likely, then we probably have to start talking about distributions and stuff like that, which is a lot more stats focused than generic probability and counting focused. So we're just going to say they're all equally likely. So if our event, we're going to call it capital E, consists of M desirable outcomes. I can't spell. How do I spell this word? Desirable outcomes. Then the probability of our event occurring So this is probably not a surprise if you know anything about probability. It's just M over N. So really what we're looking at is number of successes over number of total outcomes. That's kind of a general rule for calculating probabilities. And so I have this sort of two different terminologies here, right? Desirable outcomes versus successes. So I wrote down desirable outcomes in the definition because successes sounds like a positive thing. It sounds like, hey, whatever my outcome was positive. No, when we're talking about probability, it doesn't have to be the positive thing. Success could be a negative thing, but that's what we're interested in observing, right? So that's why I said desirable outcomes, because maybe what you want to happen is the negative thing. And success is just, I mean, this is the word that would actually be correct, but it just makes it sound like we're only focused on like good things happening, which not necessarily. So the most basic example of probability is either flipping a coin or rolling a die. So we're going to roll a die. So suppose you roll a fair six-sided die. The word fair just means it's not weighted. So that means, hey, if you roll this dice a million times, you didn't get one 50% of the time, right? It's not a trick die. No one's fooling you here. It's just a normal die. In fact, actually, does anyone know on a six-sided die, like one of the sort of important properties of it? Like if I'm looking at it and I see one in front of me, what number's on the other side of it?
6.
Right. They always add up to 7 across each other. And that's actually because the same number of dots are removed so that the weight distribution is the same on the die. So by doing that, we've made sure that it's as fair as possible. So there is a reason why we did that for dice, and it's not just random numbers. If you have a 20-sided die, I think it adds up to like 31, maybe? Or no, that doesn't. I don't remember what it adds up to, but maybe it's 26 or something. Anyway. So suppose we're rolling a 6-sided die. So what is the probability of the following situations? And these are easy to just sort of imagine. I'm just trying to connect this concept here with stuff that we can intuitively figure out. So rolling a 3. How about, what do I have here? Rolling an even number. And the last one, not rolling 3 or 5. So again, we're just asking ourselves, okay, what are the total number of desirable outcomes over the total number of outcomes overall? So we look at our die. The following outcomes are possible: 1, 2, 3, 4, 5, or 6. Right? That's what could come up if we roll a die and consider the trial a success. So rolling a 3, there's only one possible situation where we roll a 3. So the probability of that happening is 1 out of 6, right? Because there's 6 total outcomes. Rolling an even number, 2, 4, or 6. So the probability of that happening is 3 over 6, or 1/2. Not rolling a 3 or a 5. So, okay, that means it's 1, 2, 4, or 6, right? It's not a 3 or a 5. So the probability of this happening is 4 out of 6, or 2/3. So again, it's just sort of matching this concept with just how you would think. Like, you probably, if you're trying to calculate probabilities with a die, you might not even think about it, right? If I said, hey, what's the chance of rolling a 5 on a 6-sided die, people would just be like 1/6, right? Without what's the chance of getting heads if you flip a coin? It's 1/2, right? Like, we don't even think about it too much. We just know the answers. But this is really what's happening, and it extends to more complicated situations. We're just interested in number of successes over total number of possibilities. So, a couple things I want to talk about here. So there's something called the law of large numbers, and it sort of leads to a couple of conversations, and one of them is one way to determine if this is the right probability is to just do it a ton of times, right? And just write down your observations. So what is a ton of times? We're talking a lot, like not 100. For a human sitting there and just writing down the outcome of 100 dice seems like a lot. No, it isn't as far as probability is concerned. So maybe 100,000 times would be considered a decent number to see what the probability should be. And that actually can be very powerful because you can get decent approximations to the actual probability by just running simulations on what you think it should be. You kind of need to have an idea of what it should be before you can do that. So an example of why you would do that is you've got, say, a video game or something, and you're like, I think the RNG system is unfair, right? You look at it and you're like, it tells me that I have a 50% chance of this happening, so I'm going to do it 1,000 times. And I'm going to write down the outcome, and then I can do some statistics and say, okay, it actually happened. I failed 70% of the time. So then what is the likelihood of that happening? Pretty bad if the desired result is what they say it is. I saw an article about this. Sorry, this is sort of a tangent. It's related to Destiny 2. This actually just happened, where they claimed that these mods were supposed to happen on guns at equal chance. There was no weighting, and it turns out there's not weighting, but there's a weird way that the system is implemented, and it ends up being weighted. So these are situations where this sort of analysis would come in, right? You would run a simulation a bunch of times and say, hey, this does not match up with what we have seen, right? We've observed this a bunch of times, and that should not be happening if it truly is the probability that you say it is, right? So you would do this if you said, here's a fair die, and you roll it like, 1,000 times, because that's, I mean, you're a person, you can't roll it a million times. And then it comes up roughly like close to 1/6. You're like, yeah, okay, good enough, right? It's fair. So that's one way to check probabilities. But one of the reasons why I mention it is it leads to a lot of misconceptions around probability. And that's like, probability is one of those things where it's really easy to compute probabilities usually for situations we run into, but our perception and psychology around probability is really bad. There are some things that I'm sure you've heard of, like the gambler's fallacy is one of them, where you're sitting there at the slot machine and you're like, just one more pull, man. Just one more, right? Just one more. I'm going to win next time, right? No, you're not. You are equally likely to win this time as the last time, right? Because those events are what are called independent from each other. It means when you do an event, it does not matter what happened previously. The same thing is going to happen in terms of probability, right? So you could do it a million times. The next one is just as likely to have the same outcome. So no, you are not more likely to win if you have been doing it a bunch of times. You are, in the sense of, in a broad picture sense of, I have done it 100 times. So if I do it 100 more, I'll probably win. Yeah, maybe, because that's just a lot of trials and eventually you're going to win. But going into gambling, casinos are a business that make money. So if you think about it, you lose every time. There's an expected value of less than $1 for those. But that's kind of gambling in general. But that's one of the fallacies that I'm sure you've heard of, right? The sunk cost fallacy is similar, right? Of like, well, I'm already this far in. I've already tried this trial 100 times and I haven't won yet, so I might as well keep going, right? The odds say it's pretty likely that I should have it, so I'll just keep going. No, you could stop at any time, right? Especially if it's costing you money. You don't have to keep going. You could stop whenever. So that's one of the problems with probabilities. We're really bad at sort of analyzing that in the moment, right? I know that. And I have been just as guilty of sitting there with the sunk cost fallacy and being like, yeah, but I've already been here for 2 hours, so what's another hour, right? And then you do that 4 times, and now you've sat there for 6 hours, right? So I'm just as guilty for that. We're all guilty of that. It's just the human experience. But it's just, I'm mentioning that, hey, we're all bad at it. But another one that we're sort of bad at is related to this. For any single event, the probability of it happening is between 0 and 1 inclusive. So that means it includes 0 and 1. So you could have a probability of 0, you could have a probability of 1. 0 is not the same thing as close to 0. 1 is not the same thing as close to 1. That's another thing that we're really bad at as people. Again, I'm super guilty of this. So just imagine you're sitting there either gambling or playing a video game. This is most common in video games. You're sitting there, or just games in general. You're like, okay, this has a 98% chance of success. Why have I failed it 3 times in a row, right? Why? How is that possible? Because that's just probability. It's a 2% chance of failing. So yeah, you're unlucky, but nobody said that can't happen, right? In a group of like 10,000 people, that happened to some people, right? And that doesn't mean it feels good. Don't get me wrong. To be on essentially the losing end of probability sucks. It feels extra bad because it feels completely out of your control. There's random chance and you lost it, right? But it is important to realize that those things can happen, right? We've all had that experience where we're looking and it's like, okay, it's a 99% chance of success. I just failed 3 times in a row. This sucks. But we also have the opposite experience, which is a lot more depressing. But think of like a lot of medical conditions that are really serious. It's like, okay, well, it's like a 0.5% chance of happening. And then you look at the person in your life who got it. And you're like, wow, that's a super low chance of happening, but it happens to people, right? Just because it's unlikely doesn't mean it doesn't happen, right? I have celiac disease. 1% of people have it. Well, shit. I rolled the 100-sided die and it came up celiac. Oh well, that's life. And that's kind of probability, right? That's not me saying, hey, it doesn't feel bad. It's just, that's odds, baby. It's just like that. So don't get these mixed up. 0 means it cannot ever happen. No chance. Nothing will make it happen. 0.0001, unlikely, but it could happen, right? Like that could happen. It's pretty rare, honestly, for probabilities to be 0 or 1. It's honestly pretty rare. Like if I said, what's the probability of me jumping right now and making it to the moon? Well, exceptionally low, right? Virtually impossible, but I don't know. Maybe it's technically possible. Well, unfortunately, it isn't. But maybe not 0, right? So the situation where 0 probability usually comes up is when we're talking about intersection of events, like two things happening simultaneously. Like there's a probability of Travis being in that room over there, and there's a probability of Travis being in this room here. What is the probability of Travis being in both rooms at the same time? 0. I can't be. I'm not in both rooms at once. So that's a 0 probability because those are mutually exclusive events. Only one of those things can happen. Well, I mean, yeah, I could have a clone, but that's still not necessarily me. So mutually exclusive events are where that happens, right? If it's one or the other, but not both, then that's where 0 probability comes in. Probability of 1 comes in when we're kind of thinking about our total probability space usually. So if we think about it, our dice example here, each of these have a 1/6 chance of happening, right? So it's 1/6 chance to roll each of these faces. Well, that means I could roll 1, a 2, a 3, a 4, a 5, or a 6. Add all those up. It's 6 over 6, which is 1. So what that is saying is, what is the chance of something happening when I roll a die? Well, it's 1. Something is going to happen, right? I'm going to throw a 6-sided die. One of those faces is appearing, right? That's just the nature of it, right? Again, when we're talking about that, we mean successful trial, right? It being on its side or a corner is not a successful trial, so you would redo it. So if it is successful in some capacity, one of those 6 faces came up. So the probability of that happening is 1. So these kind of boil down to the probability of nothing happening, the probability of something happening, right, is usually 1. What else do I want to talk about related to sort of just this? I think that's all I've got for just like sort of general pitfalls that people fall into with probability. I guess, so like I was saying with the slot machine, the notion that when we say something, events are independent, that really does mean what you're about to do is not influenced by what you previously did. So you should think of it as every attempt is a brand new start of the trials, because they're indistinguishable from I have done a million or this is the first one, right? They're the same thing. So just be cautious of that. So anyway, back to definitions. I'm trying to sort of intersparse the dry definitions and examples with like just anecdotes, which I mean, I get it. It's like, it's late. It's late and it's not the most exciting topic to students, but I love probability. I think it's fun. So if we consider an event, let's call it A, then the outcomes not in A well, we have a symbol for that. The complement. Right, and that makes sense. These event spaces are just sets, right? It's just a set of things. So we can perform our set operations on them. So one of the reasons why this is particularly powerful is a helpful fact. And it's basically a formula. The probability of an event not occurring is 1 minus the probability of that event occurring. So why would that be the case? Well, let's just think. Right here we just said, if we consider every possible outcome, all those probabilities add up to 1, right? Something has to happen in our space. So all that adds up to 1, and we're saying, okay, the probability of rolling, of not rolling a 3 or a 5 was 2/3, or 4 out of 6. So what is the probability of rolling a 3 or 5? There's only 2 situations where that happens, so it's 2 out of 6, right? So there are 2 things that we would be interested in. If we take that away from all of the other possibilities, what we're left with is sort of the complement, right? The stuff that did not happen. So the reason why this is useful is we can also switch it around. So the probability of the event happening is actually 1 minus the probability of the complement. And this is helpful because sometimes understanding this complement is easier. So sometimes the complement is easier to work with. And I can show you an example of that real quick. But an example of where this matters is when you're trying to find, what is the probability of me having failed this many times in a row, right? So like this thing has a 30% chance of success. You just fail it 5 times in a row. You'll use this rule to say, okay, I'm going to look at the failure space and say, okay, chance of success is 30%. Chance of failure is 70%. So 0.7 to the power 5 tells you how likely it is to have failed 5 events in a row, right? So you could just use that to sort of solve those types of problems. But let me just give you like a sort of, I'll say, constructed example. They took away my clock in this room, by the way. I'm not happy about it. It's hard to keep track of time. Okay, so for this example, suppose you roll 2 6-sided dice. And you're interested in the sum. So you roll a 2 and a 3, so it adds up to 5, right? And that's what you're interested in. So what is probability of 5 being the sum? Probability. I'm really brain fried today. Probability of bigger than 2. So, okay, the way I would start this, with just our basic understanding of probability and our definitions so far, is we need to figure out, okay, how many ways can we get a sum of 5? And then to answer this question, how many ways can we get a sum of 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, right? Because that would answer this question. And then we just do that number over however many there are. So what I'm going to do is I'm going to build a table. Hopefully I have enough room here. So I'm going to write down what's the sum that we got. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So those are the sums that we could get out of a die. Makes sense. If you roll snake eyes, the lowest possible, you get 2. If you roll the highest possible 2 6s, you get 12. So anything in between. So we're interested in the number of ways to do each of these. And I'm going to sort of track the dice that we can roll. So die number 1 and die number 2, I'm going to write as an ordered pair. Because we actually want to distinguish the dice from each other. Because if the first die rolls a 1 and the second die rolls a 2, that gives us 3. But the first die could have rolled a 2 and the second die could have rolled 1. That also gives us 3. So there's actually 2 ways to do that, right? The dice are sort of separate from each other. We can't count them as the same thing. So here, okay, we want to roll a 2. Well, there's only one way to do that. We roll 1 and 1, right? We want to roll a 3. We could roll a 1 and a 2. So die 1 could be 1, die 2 could be 2. Or we could roll 2 and 1, right? There's 2 ways to do that. The reason why we need to include both is because if we exclude both, then we're actually sort of lowering the chance of this number coming up, making it lower than it actually is. Because these 2 situations can happen, right? The dice don't care that you are trying to lump them together, right? They don't care what number that comes up. Anyway, there's 2 of those. We get rolled 2 2s, 3 and a 1, 4, a 1 and a 3. So there's 3 ways to do that. And you just kind of keep going on in this table, right? So 5, well, that's one of the ones we're interested in. So it could be 1 4, 4 1, 3 2, or 2 3, and that's 4, right? So, well, we can already answer one of our questions. So that's the probability of 5 is 4 over, we need to figure out how many there are, right? Well, intuitively, we can think, okay, there's 6 possibilities for one of the dice and 6 for the other. So if we choose one of the sides, of which there's 6, associated to that are 6 more. And there's 6 ways to do that, so 6 times 6. So we expect that this is 36, but we should just keep going to confirm that. So we'll just keep going here. So 3 is 1, 2 4, 4 2, 5 1, and 1 5. That gives us 5. And 7, same thing. 3 4, 4 3, 2 5, 5 2, 1 6, 6 1, and there's 6. And then it actually starts going down now. So you can keep doing this, but the point of me writing all this down is to show something here. So 1, this does add up to 36, so great. But now we can answer this question too. Probability of being bigger than 2. So that's all of these numbers added on the top. So 2 plus 3 plus 4 plus 5 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, all over 36, which ends up being 35 out of 36. But that's a terrible way to do it, right? Because now what we had to do was we had to figure out all of these situations. I even skipped them. They're in my notes, actually, because I, for some reason, found that fun. But you have to do them to essentially answer this question if we want to tackle it this way. But this result lets us save a lot of the work, right? So this result tells us, hey, if we want to know the probability of being bigger than 2, what's the complement of being bigger than 2, less than or equal to 2? And when we're talking about complements here, we just flip those, right? We flip the sign. Okay, but then less than or equal to 2, there's only one situation. And there's only one way to do it. So it's 1 out of 36. So 35 out of 36. So if I were to, if I were just presented with this question alone, probability of bigger than 2, I only need to figure out this one. And then I can use this property and I don't have to do any of the rest of the table, right? Don't need to do it. So this is a very simple, mundane example here, right? Where it just means I didn't have to do this table to answer this question. But you can imagine situations where it's more complicated than a table, right? There's a lot of math involved in figuring out each of these cases. So then I could just do this to say, hey, I don't need to worry about those. I just need to find this one and do 1 minus that, because I know everything has to add up to 1, right? So you can save yourself a lot of effort. Okay, but we just talked about how complement applies to probability. Well, the other operations do too. So the union, this pen is kind of dying. This one is too. So the union of two events, A union B, is kind of exactly what you would expect it to be, right? So this is some collection of outcomes. This is also some collection of outcomes. So the union is just all of them kind of shoved together. So the union of two events is the event where either A or B or both happened, right? So either A or B happened, or both, right? Doesn't matter. We don't distinguish. The intersection A intersect B is the event where both happened. Where both A and B happened. So I'm just going to give you a quick and great example of that. So A is roll less than 4, and B is roll an even number. So, we can actually figure out what these are as sets. Roll less than 4, 1, 2, 3. B is an even number, 2, 4, 6. And hey, now these are just sets, right? So the operations behave exactly like they did for sets. A union B is 1, 2, 3, 4, 6. A intersect B is just 2. It's the only even number that's less than 4. Right, so these are now outcomes in an event, right? So what are the possible outcomes of rolling less than 4 and rolling an even number, just 2? That's the only thing that could happen if you wanted that to be true. Okay, but these operations end up actually leading to some more useful definitions in probability. One of them, A and B, are called disjoint, to steal the set theory word, or to use the probability word, mutually exclusive, if their intersection is empty. So these end up actually being pretty important, I would say, but well, maybe not that important. They come up often, but it's more like in sort of setting up an experiment. You would want to make sure that ideally certain outcomes are mutually exclusive, right? So when I'm talking about, Travis in room A and Travis in room B, well, that's good to know. We could talk about the probability of this. That's interesting because I can't be in both at once, right? One or the other happened. So we care about mutually exclusive events for sort of tracking things, right? It's easy when they're mutually exclusive. But the probability of either of two disjoint events happening is the sum. So probability of A union B is the probability of A plus the probability of B. This is important. Disjoint. They have to be disjoint. And we can actually sort of explain this with Venn diagrams. So if they're disjoint or mutually exclusive, that means they look like this. Here's our event A, here's our event B. So we're going to shade this one in as that color, and this one in as that color hatched the other way. Just drop stuff. So looking at these, I don't remember which one is my good one. Oh my, I'm having a day. We look here and we see that there's nothing in common, right? Their intersection is empty. So it makes sense that if this is representing a probability or like an outcome, and this one is also, that if we wanted to figure out what is the probability of either of these happening, we just add them up, right? Because they're sort of completely separate from each other. So what would happen if they weren't disjoint? So if they're not, well, what does this look like as sets? So we're looking at something like this. And again, that's the intersection. So again, we've got sort of, I'm going to shade it like that. And then the other one, I will shade the other way. We notice a bit of a problem here. This intersection we've just shaded twice, right? We shaded it green, but we've also shaded it red. So the probability of A union B, it is the probability of A plus the probability of B, but we sort of have to take away one of these, right? We have to take away one of those colors. So we take away the intersection once. So let's say we just took away the red stuff, right? So now everything is shaded in just once, right? There's no overlap there anymore. So this is the general rule if they're not disjoint, but if they are, things work out really nicely, right? I would say we like mutually exclusive events, but not that much, right? This is a nice property, but it's okay if we don't have it. There's another one that we care about way more, and that has to do with the intersection, and I'm trying to figure out where I have it written down because I kind of want to talk about it now while I'm on this topic. There we are. Wait, is that where I saw it? Yeah, okay. No, I have to talk about the other stuff first. Okay, well, that's fine. There's also the formalization of independent events, and that's the one we actually care about way more. And it turns out being independent and mutually exclusive are mutually exclusive from each other. You can't be both. So in order to get there, I actually need to talk about a type of probability that is, generally speaking, quite confusing for people. So I'll try to use like several examples to sort of explain it as best I can. So the probability of B, given that, and that's the terminology we'll use, given that an event A happened, is called conditional probability. So what this is essentially saying is that we're restricting our outcomes to B from A now. But we're saying, okay, the probability of B, given that an event A happened, so we know that A happened, so we're just going to say, okay, we're focusing on stuff in A, right? There's sort of a bigger population here, but we know that A happened, so if we're trying to really focus in on how my new event relates to having A having happened. So there's a formula here. So the notation we use is this. This line in this notation means given that. So probability of B given A happened, right? Or given that A happened. So it's the probability of A intersect B over the probability of A. So this is what I'm saying. We're restricting our attention to the outcomes in A. That's what we care about. So now our total number of outcomes is restricted to the stuff in A. And then from the stuff in A, what does it have in common with the new event B, right? So this is best seen with an example. Well, it's best seen with multiple examples, but I think I want to sort of just do one or two examples today, and then we'll do more on Wednesday. So suppose the following table has the counts of Canadians visiting Stonehenge. I know, very specific. By their language preference and region of residence. And region. And this seems very, very hyper-specific. So when it comes to probability and statistics, I do not invent examples out of thin air because I think it's a bit uncouth to invent statistics. So I pulled this out of a textbook. So they ran this survey. And why did they run this survey? Specifically to demonstrate conditional probability. This is a very, very weirdly hyper-specific thing, but it really shows conditional probability because when we think of language preference and regions of Canada, there are going to be very distinct groupings there that I don't think really represent regions of Canada when we talk about regions of Canada. So you'll see what I mean, and you'll be like, wow, okay, they did this construct this survey specifically to answer the question of conditional probability. It's a textbook question. So along the top, we have the language of choice. So going down this way would tell us how many people from that region chose that language. So there are 4 regions of Canada, as you know. There's the Atlantic region. And then there's another region of Canada called Quebec. And then there's one called Ontario. And then there's one called everything else. My favorite regions of Canada, this is what I mean. They obviously constructed this example very specifically to talk about this question. Like, imagine you're from anywhere in Canada at Stonehenge, and you look at this list, and you're like, why did you separate Canada that way? And then the person running the survey answers honestly. There's like, it's for a textbook question in our statistics textbook, and they're like, okay. That's what this is, though. 89, 70, 179, 9, 50, 4, 6, 69, and 24, 55, 93, 76, and 248. And the reason why I'm saying this is because the chance of someone choosing their language of preference being French, given that they're from Quebec, is very high. So that's why it is like. Actually, I don't believe this one either. I think they screwed that one up because this one I would expect this to be like really evenly split. This one makes sense. This one actually kind of makes sense too, being roughly evenly split. But like, I've been to Ontario. Like, this is not accurate. But anyway, they did the survey. I didn't. So, whatever. It's funny that I'm saying I didn't invent any statistics, and then someone invented a survey to invent statistics for their textbook. But anyway, so we're just going to ask some questions about this. So the first one is, I'm going to start using shorthand notation here. What is the probability that someone is a French speaker? So we answer that just like we always have been, right? We look at how many people chose French, 69 of them. How many total people are there? 248. So it is 69 out of 248, and you can actually figure out the decimal here, 0.278. When it comes to probabilities, you can write decimals or fractions. I don't care. I would say it's a good idea, because if this is bigger than 1, no, it has to be less than 1. Okay, another one. What is the probability that someone is a French speaker and is from the Atlantic? So again, we sort of look at this and we say, okay, this down here is French speakers. This over here is people from the Atlantic. So this specific number, that 9, is the people who are both, right? So it's 9 out of 248, not very many. Okay, and what is the probability that someone is from Quebec? Same thing, we just sort of look at this table here. 55 people from Quebec out of 248. Okay, pretty standard stuff. But now let's ask a conditional probability question. So the probability that someone speaks French or prefers French, given that they're from Quebec. So this is what I mean by they constructed it very specifically for this, because we expect this number to be pretty high, pretty close to 1, right? Most people from Quebec would probably select their language of choice to be French. So, okay, how do we do this? Well, there is a formula for it. Probability of French and Quebec over the probability of being from Quebec. Can't spell. Right, this is just what our formula says. Right, I wrote it earlier. This is just our formula. So now we can think, okay, probability of French and Quebec. That's 50 over 248. Over, so this is sort of our top one, probability of Quebec, we just did that. That's 55 over 248. And then we can simplify this fraction. Those denominators go away. It's 50 out of 55. So pretty damn high, right? Now, when we have a table like this, we don't actually need this conditional probability rule. We can just sort of look at it and we can say, okay, I am going to we're saying we know this person is from Quebec. So this is the only part that matters now. None of the rest of the stuff matters. We know that the person is from Quebec. So now what is the probability of French being their language of choice, given that they're from Quebec? So there's the French. Out of the total number of people is 55. So 50 out of 55 is exactly what we got using the formula, right? Now, of course, when we don't have a nice convenient table in front of us, it's a little harder to do that without figuring this stuff out. And on Wednesday, I'll have an example that sort of illustrates that. So I'll show you more about this conditional probability on Wednesday. But yeah, sort of sort of demonstrates it. Again, the idea of conditional probability is that when I have that condition, I am going to restrict my possibilities. Given that someone's from Quebec, okay, I'm only going to be looking at the people from Quebec for calculating this probability now, because I know that they're from that. I know that's what it was. What time is it? Okay. I have time for one more example, and then I'm going to do something fun. Promise. I think it's fun. I mean, look, I think everything here is fun, but I mean, this one, like, people actually think is fun. People who aren't really into math think it's fun. So there is a general rule for multiplying probabilities. And it essentially just comes from rearranging this rule. But as written, it's not actually super helpful. It is, but most of the situations we run into are not these. So, okay, this is just saying if you want the probability of A and B occurring, probability of A times this weird conditional probability thing. Okay, great. So let me just do an example here. And it kind of shows off this probability here. So suppose you have a bag of candies. Three gummy worms. I'm just going to call it gummies. I don't care. The worms or whatever you want. And 4 licorice. Find the probability of grabbing a gummy and then a licorice. So this is a conditional probability thing, even though it doesn't seem like it. So we're saying the probability of gummy and licorice. We have a formula for that. That's the probability of gummy times the probability of licorice, given that you grabbed a gummy. So the probability of a gummy is easy. We have 7 candies, and 3 of them are gummies. That's 3 out of 7, right? What about this one? Well, let's think about it. We've got this bag of candies for licorice. So we can either grab a gummy or we can grab a licorice. What we're saying is we grabbed a gummy. So that is a 3 out of 7 chance. But now, that's 2 gummies and 4 licorice. So now we see that if we want to grab a licorice from this, given that we grabbed a gummy, we have to follow this path, right? It actually matters where we go, right? This is the conditional probability. Here, if we did licorice, this is grabbing a licorice, given that we grabbed a gummy just now, right? So this here is 4 out of 6. So then all told, this probability is 3 over 7 times 4 over 6. Which is whatever it is, right? The actual number doesn't matter that much. So you can see, actually, if you swap the order here, the numbers would change, right? If you said grabbing a licorice and then grabbing a gummy, that will change the number here. And so it'll change the probabilities. At least the calculation. The probabilities might be the same. They might be equally likely, but it does change that. So, okay, this is not super great because calculating this conditional probability is kind of weird. Either you need to do some kind of flow chart like this, or you need to really think about what's going on. So we need something called independence. Two events, A and B, are independent if, this is a really funny thing, it's essentially, people looked at this and they were like, hey, it kind of sucks that we have to calculate conditional probability, so let's make a definition that's nice when we don't have to. So when this thing is the same as this, so essentially you can get rid of the conditional probability. And now this actually does match up with the intuitive definition of what it means to be independent, in the sense of, well, think about it. If these are the same thing, what this is saying is, if we want to find out the probability of just event B happening, that's the same thing as if A happened first and then B happened. Right? It doesn't matter that A happened, right? They're the same probability. So that makes sense to call that independent, right? An event happened, didn't affect the next one. But that means for independent events, P of the intersection is just multiply the probabilities. This one we care about the most. We almost, I don't want to say always, because there's a lot of statistics where we don't talk about independent events, but if you're like learning statistics for the first like 2 years, you're going to be talking about independent events, always. You're going to say, suppose this is an independent random sample and these are independent events, right? Because it means this rule happens, which is very, very convenient. So general rule, the word or means add, and means multiply for probabilities. Again, it requires mutually exclusive, independent. These two things are, they can't be both. So if we think about it, and this doesn't really matter very much, this is just sort of me saying it. If A and B are disjoint, so these are our two events, can they be independent? Well, that would mean the probability of B equals the probability of B given A. But what is this probability? So this is the probability of A and B over the probability of A. Hey, wait a minute, the probability of A and B is 0, right? It's empty. But this is obviously not 0. So if they're disjoint, they can't be independent. So that's just sort of an aside. Independent events are not the same thing as disjoint events. In fact, they couldn't be more opposite of each other, because you can't be both. If you're one, you can't be the other one. So that's just a sort of an aside. Now, I do have one more example to talk about related to conditional probability, but I'm going to save that one for Wednesday to warm you up to it, because I want to talk about something fun.